What if the greatest show in the universe is a disappearing act? Imagine looking up at the night sky, a tapestry of countless galaxies, each a city of stars. Now imagine them all rushing away from us faster and faster until they vanish beyond a cosmic horizon, lost forever. This isn't science fiction, it's the reality of our expanding universe, driven by a mysterious force that astronomers call dark energy. It is, honestly, the most profound mystery in all of science, a cosmic ghost that makes up nearly 70% of everything that exists. We can't see it, we can't touch it, but we can see what it does. It's pushing space itself apart, a relentless universe-wide expansion. This cosmic acceleration is a relatively new discovery. For most of the 20th century, we thought the universe was in a great cosmic battle with itself. Gravity, the force that pulls everything together, was locked in a tug-of-war with the outward momentum from the Big Bang. We pointed our telescopes at distant supernovae, exploding stars that act as standard candles, to measure the expansion rate and settle the debate. For a long time, our best guess was that dark energy was a constant, a fundamental, unchanging property of space itself. Albert Einstein had once imagined such a thing, calling it the cosmological constant. He introduced it to make his equations describe a static, unchanging universe, which was the prevailing belief at the time. When Edwin Hubble discovered the universe was, in fact, expanding, Einstein famously called it his biggest blunder. But history has a funny way of coming full circle. When astronomers discovered the universe's expansion was accelerating, Einstein's blunder looked more and more like a stroke of genius. The idea was simple and elegant. If dark energy was the cosmological constant, it meant that as space expands, more of this energy simply comes into being, filling the new volume of space. Think of it like a magical dough that rises, but instead of the yeast getting spread thin, new yeast appears everywhere to keep the density exactly the same. This constant push would explain the accelerated expansion perfectly. It would be a fundamental law of nature, as reliable and unwavering as the speed of light. This became the standard model of cosmology, a framework that fit our observations beautifully. The lambda stands for the cosmological constant. In this scenario, the expansion would accelerate forever. Galaxies would recede from us at an ever-increasing pace, their light stretched into oblivion. The universe would become colder, emptier, darker, heading towards a big freeze, heat death. To peer into the universe's history, we built a remarkable time machine. It's called the Dark Energy Spectroscopic Instrument, or DESI. Perched atop a mountain in Arizona, DESI is a robotic marvel, a collection of 5,000 fiber optic eyes that can stare at 5,000 different galaxies at once. Over the next few years, it will create the largest three-dimensional map of the cosmos ever attempted, capturing the light from tens of millions of galaxies. By measuring how much their light has been stretched, or redshifted, DESI can chart the universe's expansion history with breathtaking detail. And its first year of data has given us a tantalizing hint that something is afoot. The initial findings from DESI suggest that dark energy might not be the constant we thought it was. The data seems to point to a possibility that dark energy's behavior has changed over time. To understand this, scientists use a number called W, which is the equation of state parameter. It's a simple ratio. The pressure dark energy exerts divided by its energy density. If dark energy is Einstein's cosmological constant, then W must be exactly -1, forever and always. Any deviation from -1 means that dark energy is dynamic, and the story of the cosmos gets a whole lot more interesting. The new evidence hints that in the distant past, dark energy may have been different. It might have even crossed a critical boundary known as the phantom divide. This is the line where W equals -1. The data suggests that dark energy might have evolved from a state where its W value was greater than -1 to 1, where it is less than -1. Imagine a force that was once acting like a gentle, constant push, but then transformed into something else entirely. This is a subtle statistical hint, not yet a conclusive discovery, but it is one of the most exciting developments in cosmology in decades. Why is this shift so important? If dark energy can change, it means its role in the universe might not be fixed. It could mean that dark energy was once a force that helped slow down the universe's expansion, working alongside gravity, before it reversed its role and began driving the cosmos apart. It's as if one of the fundamental rules of the game changed mid-play. This isn't just a minor tweak to our models, it's a potential revolution in our understanding of the universe's fundamental components. The cosmic story might have a plot twist that no one saw coming. This potential shift in dark energy's nature forces us to reconsider everything we thought we knew about the destiny of the cosmos. If dark energy is not a constant, then the Big Freeze is no longer a certainty. A dynamic dark energy opens the door to other, more exotic fates. For instance, if dark energy's repulsive force grows stronger over time, a scenario called phantom energy, it could lead to a big rip. In this dramatic end, the accelerating expansion would become so powerful that it would overcome not just the gravity holding galaxies together, the forces holding stars together, the forces holding planets together, and even the forces holding atoms themselves together, tearing the very fabric of reality apart. Conversely, if dark energy could weaken or even switch back to an attractive force, the future could be entirely different. The universe's expansion could slow, halt, and reverse, leading to the big crunch we once thought was a possibility. The cosmos would collapse back into a hot, dense state, perhaps even igniting a new Big Bang, a cosmic cycle of birth, death, and rebirth. The DESI results, while preliminary, are like the first tremor that signals a possible earthquake in our understanding. They remind us that the universe is far stranger and more wonderful than we can imagine. With each new observation, we pull back the curtain just a little bit more.